Was it Kiran or Roshan? I don't know your voices. I'm sorry. So, who was asking another question? Or was
Yeah,
it
I
you?
was
You were
yes, sir.
asking. Yeah, go ahead.
Yes, sir.
Yes.
So I just wanted to understand this, that when we are working, say, on a compact Lie group, we understand that all these notions actually coincide. In case of, say, nilpotent Lie group, as you just pointed out, that say for Heisenberg group or something like that, these exponential maps are having different, they need not coincide. Okay. And
Right.
so, like, some other spaces also I've seen, like, say, atomic spaces or harmonic connectives. They also have seen similar statements that the exponential map is actually a global isomorphism from the algebra of that particular to the space. So in that sense, also like there is a invariant Riemannian metric over there, right? And so I want also to see that whether these notions coincide with the
Your voice is again, it's become, I can't hear it anymore.
absolutely.
Now I can hear. Yeah, yeah.
Yes, in case of diametric spaces, there
In
is also
case of what spaces?
diametric spaces.
What Banach spaces?
Right.
No, can you write in the chat, please? I can't hear. Sorry. Oh, Damic-Ricci spaces. Okay, yes. So what do you want to say about Damic-Ricci spaces? Yes. So finish the question. There again, you have a left invariant metric, but I mean, the exponential map is not the same as the Lie group exponential is not the same as the Riemannian exponential. So it coincides, for example, along certain subgroups. So along the AT, yeah, X is an analytic diffeomorphism. That is true. That's just because it's a product, right? I mean, topologically, it's a product. So n cross A. So and from n to little n to capital N is a diffeomorphism. From little a to capital A is just the usual exponential from R to R. So this will be a diffeomorphism. But the Riemannian exponential in this case is also a diffeomorphism. But that's because Damic-Ricci spaces are non-positively curved. And so we have the Cartan and Hadamard theorem, which will tell us a simply connected, non-positively curved. Yes, the two exponential maps are different. Yes, they're different. Yes. Because see, just apply it to an element of the nilpotent group, then the one parameter subgroup you get, it lies in what's called a horosphere. Like
Yes,
if I look at NT, it lies in a horosphere. There are no geodesics lying in a horosphere in a Damic-Ricci space. There are no geodesics lying in a horosphere.
Sir, by horosphere you mean a complete orbit of nilpotent?
I mean the orbit of the nilpotent group, but there's a geometric. We'll give a geometric description of horospheres in terms of what are called Boseman functions. So yeah, there's a purely metric description of horospheres. Those coincide with the n orbits and the translates of the n orbits. Yeah.
So in case of a Riemannian or pseudo-Riemannian manifold, if it is analytic, then the exponential map is analytic if and only if the Riemannian metric is analytic and it finds
well, I'm not sure about if and only if, but probably if and only if. Yeah, at least one direction. Okay. If the metric is analytic, then the exponential map is analytic. That's true.
Yeah, it is sufficient.
Yeah. Probably the converse is also true. I think you can write the Riemannian metric in terms of the exponential, and yeah. So right. I think the converse is also true. Probably.
And these two notions of exponential coincide when the metric is binary. That's what you say.
Right. For your Heisenberg group or for the Damic-Ricci spaces, for your solvable Lie groups, these will be different exponentials. These will be different.
Okay, sir.
Yes.
Only in case of compact league group, the situation is very nice.
Right. Exactly.
Okay, sir.
Exactly.
Thanks.
Yeah.
In case of that also, that the
Well, one thing I can say for the Dimitrici spaces, if I look at the AT subgroup, then the AT group is both a Riemannian exponential and a Lie group exponential. The AT one parameter subgroup
is just rank one, so the things going.
No, but that AT subgroup is a geodesic, so it's also the image of the Riemannian exponential. It's a geodesic. So, I mean, normally one parameter subgroups are not geodesics, right? That's the point. I mean,
Yes.
one parameter subgroups are not geodesics in general. So, if they were geodesics, then the two exponentials would be the same. Then the two exponentials would be the same. Yeah. So the question is really, when are one parameter subgroups geodesics? That's the
Right.
question. That's
Boils down. Yes.
Yes.
Okay. So anything apart from say compact league group, any other familiar nice spaces where these things actually coincide? Can we see examples?
I can't think of any. Those are the only Lie groups I know for which they coincide. So yeah.
Then maybe they are the only ones.
Right. Yeah.
Okay.
You normally you don't have bi-invariant, because if you have bi-invariant metric, then the no, the Lie group doesn't have to be compact, but doesn't have to be compact, but yeah, I can't think of other examples except for compact groups, really. I can't think of other examples. I mean, it'll have to be close to abelian. It'll have to be close to abelian. So, yeah. Either compact or compact cross abelian or something like that. So, yeah.
Something like those. If we can make sense of these on the compact extensions on Euclidean spaces like Karta motion group or those.
Right. Possibly, yeah. I mean, what you want is that the image of add should be compact, right?
Yes. Then we can. Then that argument follows in case of
right. Yeah, you want the image of add to be compact. So that's it.
Thank you.
Okay. All right. So let me share the screen and get back to the notes. Okay. So we make a definition now. We know that xq is the exponential map is a diffeomorphism in a small neighborhood of the origin in the tangent space. So such a small neighborhood of the origin in the tangent space at Q maps to a neighborhood of Q. So we will call such a neighborhood a normal neighborhood. All right. So a neighborhood of P and M of the form X sub P of V, where V is an open set containing 0 in the tangent space, such that XP restricted to V is a diffeomorphism. Such a neighborhood is called a normal neighborhood of P. Okay. And if I take a ball inside this open set in the tangent space, say a closed ball, B epsilon 0 closure contained in V, then the image of this ball is called the geodesic ball with center P and radius epsilon. Okay. So like in this picture here, if so, I mean, what do I mean to say here? So if I take a ball of radius epsilon, what is the length of these curves? The x of TV. So here, if norm V is equal to epsilon, right? Suppose I take a point V here. So then I can look at the curve going from 0 to V, right? And I want to calculate its length. So that curve will be basically T in the interval 0, 1 maps to TV. And then this is in, say, TQM. And then that maps to X sub Q of TV in N. So if I call this, say, gamma T, okay, then I know that the speed of, this is a geodesic, so its speed is constant. So norm gamma prime T, this is constant equal to norm gamma prime 0. And gamma prime 0 is, I know, V. So this is norm V, which is epsilon. So the length of gamma, this is the integral from 0 to 1 of norm gamma prime T dt is just the integral from 0 to 1 of epsilon dt. So this is epsilon. Okay. So these curves have length epsilon. Okay, these curves have length epsilon. So So now what I want to do is I want to think of my Riemannian manifold. I want to turn it into a metric space. So I want to define a distance between pairs of points. Okay. So the natural thing is to imitate what we do in Euclidean space. The distance between any pair of points is the infimum of lengths of curves joining those points, right? So we can use that as the definition for the distance function in a Riemannian manifold. Okay. So we're going to do that. And so then if I look at this geodesic ball, then the geodesic from P to any point in this geodesic ball, this geodesic to any point in the geodesic ball, this has length at most epsilon. So that means these points are within distance epsilon, right? These points are within distance epsilon of the point Q. And so this should be contained in the ball of radius epsilon around Q. And what we will say is actually this is equal to the ball of radius epsilon around Q. So I won't do the full proof of that. We'll see the full proof later, but I'll do part of the proof. So the point is that geodesics, these are locally length minimizing. So this is what the next proposition says. So let B be a normal ball with center P in a normal neighborhood U of P. Okay. So that means B is the image of a ball in the tangent space at P, where the exponential map is a diffeomorphism. And let gamma be a curve in this normal ball from the interval 0, 1 to B, let it be a geodesic with gamma 0 equal to P. Then for any piecewise differentiable curve C from 0, 1 to M with C0 equal to P and C1 equal to gamma 1. So with the same endpoints, P and gamma 1, we have that the length of C is greater than or equal to the length of gamma. And equality implies that C of 0, 1 is equal to gamma of 0, 1. So equality implies that the two curves are the same. Okay. So this uses something called the Gauss lemma. So that takes a bit of work to prove. We'll prove the Gauss lemma later when we talk about the tangent bundle, the structure of the tangent bundle. It will follow as a consequence of some other things that we'll do. So let me assume the Gauss lemma and then give you a sketch of the proof of this proposition. So, okay. So, all right. So this is B epsilon 0 contained in TPM. And then I have XP. And then I have its image. And then I'm calling B, which is the image of this ball in the tangent space. This is XP of B epsilon 0. This is a normal ball, normal or geodesic ball. So here's the point P. And then I'm saying if I take a geodesic here, say this is gamma 1, and this is gamma 0. And then I take a curve C, which also has the same endpoints. So gamma 1 is equal to C of 1, and gamma 0 is equal to C of 0. Okay. Then the claim is that the length of C is greater than or equal to the length of gamma. Okay. So to prove this, we need the following Gauss lemma, which says the following. So suppose I have a point V here in this ball in the tangent space. So this is a tangent vector. Okay. So, okay, let me not draw it in the same picture. So let me just, so let me draw you a picture. So this is B epsilon 0 in TPM. I take the origin. I take a non-zero vector V. And then I take a vector W which is perpendicular to V. Okay. So then I think of W as a tangent vector at V, right? This TPM is a vector space. So any vector in the vector space, I can put it at any point in the vector space. I can think of it as a tangent vector at V, right? So suppose these two are perpendicular. Then what the Gauss lemma says is that under the exponential map, if this is so this is P, and this is XP of P. So then if I think of W as a tangent vector at V, I can apply the derivative of the exponential map at V, right, to this tangent vector W. So what the Gauss lemma says is that this derivative will be perpendicular to the vector, the tangent vector to this geodesic. So if this XPV is say gamma 1 and this is gamma prime 1 and this vector here is DXP at V of W, okay, then these two will be perpendicular. Okay. Is the statement clear? So say V belongs to B epsilon 0 minus 0 subset of TPM. W is an element of TPM which we identify with the tangent space at V2 TPM, and W is perpendicular to V. Then the inner product between DXP at V of W and DDT at T equal to 1 of XP TV. So these are both tangent vectors in the tangent space at the point XP of V, right? So this is 0. So these two vectors are orthogonal. Is this clear? The statement? So we'll prove this later, all right? So now let's prove the local length minimizing property of geodesics. Okay. So what we do is we basically use a decomposition of vectors into polar coordinates, a radial and a tangential direction. So let me call the exponential map F, and so this is B epsilon 0 in TPM, and so this is the origin, this is P. Okay. So I have my gamma, my geodesic, and I have my other curve, C, which could do something strange. So C might go out of this ball B also. B is equal to f of B epsilon 0. So this F is a diffeomorphism. So let's first assume C is contained inside B. So I'm abusing notation. I mean the image of C is contained inside B. Okay. So then I can define a curve C tilde, which is F inverse of C. So this will be contained inside the ball in the tangent space. So this will start from 0 and this will be some curve here. Okay. So this is C tilde. Okay. So then what is the length of C? This is the length of, so C is now F composed with C tilde. So this is the integral from 0 to 1 of the tangent vector to F composed with C tilde. So this is the norm of, by the chain rule, dF at the point C tilde of t applied to C tilde prime of t dt, right? Yes. Okay. Yes, are you there?
Yes.
Yeah, so up to here is fine. Yeah. Now what do we do? Now what I want to do is, I look at this point. So so this is C tilde of t, and I have here this tangent vector. This is C tilde prime of t. And what I do is I break up this tangent vector into a radial component, okay, and an orthogonal component. All right. Yes, if this is C tilde t, then I break it up into a component which is proportional to the vector C tilde t, and which is orthogonal to the vector C tilde t. All right. So I write this as C tilde prime t tangential component plus a normal component. All right. Is this clear? Okay, so C tilde prime t. So I'm doing this in brackets. This is equal to C tilde prime t tangential plus C tilde prime t normal, where C tilde prime t, the normal component, is perpendicular to C tilde T. Okay. All right. Yes.
Yes.
So this implies by Gauss lemma the inner product between df at C tilde T of the normal component C tilde prime T normal component together with ddt at T equal to, oh no, let me call it DDS, sorry. DDS at S equal to 1 of F of S C tilde T this is equal to 0. All right. Okay. Yes. So now what happens? So this becomes equal to an integral from 0 to 1 of the norm of, so df is a linear map, so df at C tilde T of the tangential component. So what is the tangential component? The tangential component is the inner product of C tilde prime T with the unit vector in the direction of C tilde. So C tilde T over norm C tilde T. Into C tilde T over norm C tilde T. So this is the component in the direction of C tilde, right? Plus df at C tilde T of C tilde prime T normal component dt. Okay. And now note that df, if I look at this point, let's say CT here. So suppose this point is CT. If I look at the geodesic passing through CT, right? So this point is CT. Then DF will map the tangential component in the direction of this geodesic, and by the Gauss lemma, it will map the normal component to some normal vector, right? This will be the image under DF. Is that clear? Yes? So therefore, these two vectors here, the images under DF, these two are orthogonal. This and this, these are orthogonal. By Gauss lemma. Is it clear? Yes? Is it clear?
Yes, sir.
Yes. And so this, therefore, this norm will be greater than or equal to the integral 0 to 1 of just the norm of the tangential component. Okay, so I can forget about the normal component because that will only increase the length of the tangent vector. And now what do I know about the exponential map? I know that in the radial direction, this preserves lengths of tangent vectors in the radial direction, right? Because note what is, if I take a vector v, this is the origin, and I think of v as a tangent vector at v, right? Then what is df at v of v? What is the norm of this? This is the norm of ddt at t equal to 1 of x sub p of tv, right? Yes? Right?
Yes, sir.
And this is a norm of gamma prime 1, where gamma is the geodesic with initial condition v. And so this is the same as norm of gamma prime 0, which is the same as norm v. Is it clear? So in this direction, it preserves the lengths in this direction, in the radial direction. All right. So this length will be the same as what the length of what's inside. So this unit vector will disappear. So we've got less than a minute. Let's end the meeting and let's start and I'll finish in another 5-10 minutes. Okay. So let's stop now and let's